Have you ever had a bad day? The kind of day where you get an F on your English paper, and then while you're trying to put it back in your backpack, you get a paper cut and it gets infected, and then you shout out a curse word whenever you get home, and then your mom hears you? That kind of day where you end up with maybe a bar of soap in your mouth because of the word that you just shouted out? Well, if you've had that bar of soap in your mouth before, you've already experienced one of the many properties of acids and bases. Let's talk first about acids. Acids have a sour taste. In fact, the Latin word acere is the root word for acid, and this word means sour. So acids were typically classified because of that sour taste. They have a pH of less than 7, and they turn litmus paper red. They also have a watery feel. If you were to dip your hand in some acid, which I don't recommend, then you would notice that they feel a lot like water. They conduct an electric current, which makes them electrolytes, and they will react with bases in a neutralization reaction. They also react with active metals in a single replacement reaction, producing bubbles of hydrogen gas. For example, if you were to take hydrochloric acid and put some magnesium ribbon into it, you would form magnesium chloride, which would dissolve into the solution, but also hydrogen gas, which would rise to the surface as bubbles. Bases have some different properties than acids. That soap that we were talking about a minute ago that you just had your mouth washed out with, that's a base. And one of the properties of a base or an alkaline substance is that it has a bitter taste. Soap doesn't taste very good. It also has a slippery feel. Another place that you would have noticed the bitter taste of a base would be in medicines. A lot of those medicines, over-the-counter cough syrups, things like that, have bases in them as active ingredient. And those bases have a bitter taste, which is why the manufacturers of the medicines add flavoring. And you'll see it advertised on the bottle, great grape flavor, or tastes like real cherry, things like that. Other properties of bases are that they have a pH greater than 7. They turn litmus paper blue, they're corrosive to skin, and they're poisonous. It's a common misconception that bases are relatively harmless compared to acids, that acids are the dangerous ones. The truth is that they're both not really that safe to be around, depending on which ones you're looking at. But the bases are actually more corrosive to body tissues than the acids are. Something like bleach, you wouldn't want to sit there with that on your skin. They're also poisonous typically if you ingest them. Bases conduct an electric current, which makes them electrolytes, and they react with acids in neutralization reactions. To summarize the properties, you'll notice that acids have a sour taste, whereas bases taste bitter. Acids have a watery feel, whereas bases feel slippery. Both of these types of substances form electrolytes in solution, which means that they conduct an electric current. The pH of an acid is less than 7, whereas the pH of a base is greater than 7 on the pH scale, which typically ranges from 1 to 14, but does go outside of that range. Acids turn litmus paper red, whereas bases turn litmus paper blue. Acids are going to react with metals. Bases are going to react with your skin. Both of them will react with each other in a neutralization reaction. Some examples of acids, things like sulfuric acid, H2SO4, is used in batteries. It's battery acid. Phosphoric acid, H3PO4, is used in this bottle of shower power, which fights soap scum on the glass of your shower. Hydrochloric acid is a common find in your pool supply store because it's used to maintain proper chemical balance in a swimming pool so that you don't have algae and that type of stuff growing in the water. Nitric acid can also be used in maintenance of lawn or plants to maintain the proper pH balance in the soil. Some examples of bases. We have some Easy Off oven cleaner, which contains sodium hydroxide. We have some hair relaxer by Chi, which contains calcium hydroxide. Milk of magnesia, which contains magnesium hydroxide. This is an antacid. Potassium hydroxide, KOH, which is a common ingredient in hand soap. Arrhenius acids, we've talked about how to name these already. An arrhenius acid is simply an acid that has hydrogen at the front of the formula, and they're defined as hydrogen ion donors. A binary acid is one that has only two elements in it, so it's hydrogen plus a non-metal element. For example, hydrogen and chlorine, we get HCl. If we want to name a binary acid, the names of all of these acids begin with the prefix hydro. After that prefix, the acid is named after the anion with the ending changed to -ic. So for example, HCl becomes hydrochloric acid because it's named after the anion chloride. Oxyacids, on the other hand, are hydrogen plus a polyatomic ion. Those polyatomic ions contain more than one element, and then of course you have hydrogen there as well, so they have at least 3 elements in an oxyacid, and they're called oxyacids because they have oxygen. Those polyatomics pretty much all have oxygen in them. If you want to name an oxyacid, you're going to name the acid after the polyatomic. No prefix. You just change the ending of the polyatomic depending on whether it ends with -ate or -ite. So for example, H2SO4, which is hydrogen and sulfate, becomes sulfuric acid because the ions that end in -ate are changed to -ic. H2SO3, on the other hand, becomes sulfurous acid because the ions that end in -ite are changed to -us when writing the acid name. An arrhenius base is a salt containing a metal plus the hydroxide polyatomic ion. For example, NaOH. The naming rules for an arrhenius base are that you name the metal first, a Roman numeral needs to be used if it's a transition metal, and that you end with hydroxide. NaOH, for example, is called sodium hydroxide. CuOH2 is copper 2 hydroxide. In this instance, we need a Roman numeral because copper is a transition metal. It's in the middle of the periodic table. And the Roman numeral must be used to show the charge of that transition metal.